In this video we're going to take a look at the Ransom challenge on HackTheBox. It's an easy reversing challenge, and the description says, we received an email from Microsoft support recommending that we apply a critical patch to our Windows servers. A system administrator downloaded the attachment from the email and ran it, and now our company data is encrypted. Can you help us decrypt our files? So I've already got the files downloaded into the local directory, so let's go and do some basic file checks. So if we check the file types, we'll see that we've got a Windows Update exe, 32-bit executable for Windows, and we have this login spreadsheet which looks like it's been encrypted. So let's just print out the login spreadsheet. And one thing we'll instantly notice is we see this super secure string which is repeating throughout the file. Let's have a look at the Windows Update. So we could look for strings greater than 10, but we're going to get quite a lot of output here, too much really to sift through. For a quick win, you could try to grep out something like HackTheBox, but we're not gonna get anything there. So probably the best solution here would be to move over to the Windows system, seeing as we're dealing with a Windows executable. But I personally hate Windows, so I'm going to open up ghidra here and let's see if we can reverse engineer it and stay inside Linux. I'll create a new project here. It takes a little bit of time, so I'll speed through the process. So if we go straight to our functions section, and we might want to have a look here for decrypt, but there's no sign of anything. We do have an encrypt and encrypt file functions, so they're likely to be of interest, but let's have a look at the main function first of all. So we can see here that it takes two arguments, and if there's only one argument provided, it'll set the directory as the C users directory. Otherwise, it'll take the directory, I guess, and the file name from the user, and then it's going to call this ftw function with those parameters. So if we have a look at this function, there's actually quite a lot going on in here. So I saw this and immediately backtraced to the encrypt file function, which is likely to be what we're interested in. If we take a look at that, we'll see that we have a read file function call with the file name would be passed as a parameter, and then it calls encrypt to encrypt the file, and then it writes the file again. So let's take a look at the encrypt function. And at the beginning we have some variables declared. We have some values then which are assigned to those variables on the stack. So this is a hex value, but if we go over to our disassembled code here, we can highlight it and see what that equals in decimal and in char as well. So we can see that the char there is actually, if you reverse that, it's showing super secret, although it doesn't have the full string there. The rest of it is down here and here. So essentially these values together will equal the super secret in capital letters, which we saw throughout the Excel file. Remember, if we print out that login, we see this super secure throughout, so that appears to be the key which is being used. And then we have this local C which is set to 0, which looks like it's going to be our loop counter as well. So this loop looks a lot more complicated than it is because of the casts that we have here, this ulong, long, 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 and all these char pointer casts. Make it look pretty confusing, but essentially we have a loop here which is looping from 0 through to param2, which param2 is equal to this value right here. So if we highlight that, we can see it's a large decimal value, and it looks like essentially it's going to loop through this many times or until the file has encrypted. So presumably if there's more than this many bytes in the file, it won't be able to encrypt it all. So it'll loop through each time. We have the local 0, which starts off at 0, local C, sorry, starts off at 0, and this param1 is the file that we've loaded in. So at the beginning it's going to take the byte at the 0th element, and it's going to assign it to equal the local 17 plus local C. Just ignore these long stuff. So local 17 plus local C, which again is this 0. So essentially we're looping through, we're taking one byte here, then we're taking the next byte, and we're doing the same from the file as well. So on each loop iteration we take the next byte from the file, the next byte from our key, and then what are we doing with that? Well, it looks like all we're actually doing here is an addition. So this modulus is just ensuring that once we get through the secret key, it'll start again at the secret key. So it's going to loop through, and this is looping through 11 times because there's 11 characters in our key. And each time it goes through, it's assigning then the value on the stack to equal, or the value from the file to equal itself plus whichever value in the key it's currently iterating through, which is what we have here. So param1 plus local C plus the local 17 local C. So for our first element, assume that the file begins with the capital letter A, which would be 41 in hex. It would take 41 from the file, and it would take 43 from the key. It would add them together, and then it would write out the result, and it will loop through until it's done that throughout the whole file, and then write that again. So this would explain why we see this super secure so much throughout the file, because if it loads in a byte which is null, if it's zeros, it's simply going to add the character S and then U, etc. to that, which will just, because you're adding S to 0, it's just still going to equal S, and that's why you're seeing the key repeat so many times throughout the file. So there's a few different ways you could do this. I mean, the easiest way would have probably been to move over to Windows and to run this in a debugger and see what was actually happening with the addition. But now that we know how this loop's essentially working, we could just go and write a Python script to decrypt it, which is how I went about solving the challenge. You could also potentially patch the binary. So in the last video we went through some binary patching with inside ghidra and in Pwn Tools. So you could patch, for example, these values, and rather than the key being super secure, you could have the key as being super secure minus super secure, so that whenever it's adding the value here, it's actually subtracting, and that would get you back to your original decrypted file. Or you could modify this loop, modify this condition so that you essentially have a decrypt function, and then you just be able to call the program in Wine if you're inside Linux, or move over to Windows, call the program with the encrypted file, and that would produce the decrypted file. But I found that doing this in Python was an easier way, or at least I thought it would be anyway. So let's go and see how I solve this. So I've already got a Python script here. Let me copy it over. I'll call this decrypt.py. And it's a very simple script. So we have our key here, which we know is super secure. We have our file, which we're reading in. I imported Pwn Tools here just to make the you can use this read and write function. In fact, let me quickly go to I find that Pwn Tools can be particularly handy for converting things in Python. So if you go to the tutorial here, Pwn Tools tutorial, you can see that there's a lot of functions in here for converting between base64, URL, hex. Although, having said that, I still kind of struggle with this. I would say that putting together this script took longer than identifying what needed to be done, because I was trying to convert between bytes and strings and decimals to do the calculations, and it really wasn't working out too well for me. So let's see this running. Just first of all, I'm just going to comment this out. Let's just print out the encrypted. So if we read in this file, let's run that Python decrypt, and you'll see here then it's given us all the hex values. So I can now loop through each one of these bytes, which is exactly what we've done here, and just set up some values to initialize to as a loop counter, and then to hold our, not our flag, but our decrypted bytes anyway. And we're looping through each byte in the encrypted spreadsheet, and then we're saying that the byte should equal itself minus the current character in this key. So we just have the same modulus there. Let me try and bring this back over. See if we can compare them. So we can see it right here. This is just basically the same loop. We're looping through each byte in the file, just like we are here. We have our key defined right here, just like we do in ghidra, and then we're looping through, and each time, instead of saying we want to add that, we're now saying we want to subtract it, and that'll give us our decrypted. So we could then create an encrypt function as well, and we could have this so we can easily encrypt and decrypt files. So essentially done that, we're looping through to make sure it keeps going through the key, and then at the end we print out the flag. Now let me try and run that now. Oh, So note that this obviously isn't in the correct format for us to save it to the decrypted spreadsheet file. So again, I was having some problems in terms of converting these to bytes. I'm not too sure in terms of them being some of them being negative integers. If somebody knows a quicker, I'm sure there's a very quick and easy way to just subtract these values from each byte in the file. Maybe a better way than I'm doing it. So if you have a different solution to this, I'd be interested to hear it. But what I did now is move over to CyberChef just to finish this off. So I'm going to take a copy of this array of decimals and then open up CyberChef. I'm going to convert from decimal. Paste this in here, you'll see we get it's not a valid byte array, which is exactly what I was getting in Python. Let's change that to supported values, and we'll see here we have the PK extension, which looks good. We're seeing in here the rels, which is typically the kind of structure you would see for, and here's our worksheet. So it's looking good. It all looks like that's in the right format. So now we can just go ahead and save the output to a file. So I'm going to save this to decrypted.xl. What is it? XLSX. XLSX, yeah. So we'll save that. I should have opened that really. Okay, so let me go to downloads and open that up, and we'll see that we now have our flag. So it wasn't too hard to find that. It took me longer to work out the converting between bytes and strings and decimals in Python than it did actually work out what needed to be done. But as I say, you could also have solved this in Windows, perhaps using a debugger or by patching the binary or just going through and manually decrypting as need be. But I hope you've enjoyed the video. If you have any questions or comments, leave them down below. Thanks.